Why is filter order important for IIR filter design? Have you ever wondered why the order of a filter matters so much in infinite impulse response filter design? Let's break it down in a way that makes sense. The filter order refers to the number of reactive components in the filter or the degree of the filter's transfer function. This directly impacts how well the filter can separate the signals you want from those you don't. IIR filters use feedback, which means their output is influenced by both current and past inputs, as well as past outputs. This feedback mechanism allows IIR filters to achieve a desired frequency response with fewer coefficients compared to finite impulse response filters, which do not utilize feedback. When you increase the filter order, you generally enhance the filter's performance. A higher order allows for a steeper roll-off at the cutoff frequency. This means the transition from the passband, where signals are allowed through, to the stopband, where unwanted frequencies are blocked, becomes sharper. This sharper transition is essential for applications requiring precise frequency selectivity. Moreover, a higher filter order can provide better attenuation of unwanted frequencies. It allows the filter to more closely approximate an ideal filter response, which is often the goal in signal processing tasks. However, increasing the filter order comes with its own set of challenges. One major concern is stability. Since IIR filters relying on feedback, higher-order filters have more poles in their transfer function. These poles must be carefully placed within the unit circle in the complex plane to maintain stability. If they are not, you may encounter issues like oscillations or divergence in the filter's output. Another challenge is the increased design complexity. Higher-order filters requiring more computational resources and careful numerical methods to design and implement. This can make the design process more time-consuming and complicated. Additionally, higher-order IIR filters can introduce phase distortion. This means that the phase response of the filter may become nonlinear, which can be critical depending on your application. For instance, in audio processing, phase distortion can affect sound quality. From an electrical engineering perspective, filter order is a key design parameter. It balances performance with practical constraints. For example, a low-order IIR filter may not meet strict frequency selectivity requirements, while a very high-order filter could be unstable or too resource-intensive. In real-world applications, such as telecommunications and control systems, designers often aim to select the minimum filter order that meets the required frequency response and stability criteria. Classical IIR filter types, like Butterworth, Chebyshev, and elliptic filters, provide different trade-offs. This allows engineers to optimize filter order based on specific needs. In summary, filter order is vital in IIR filter design because it affects how well the filter meets frequency response specifications, influences stability, and impacts computational efficiency. By carefully selecting and designing the filter order, engineers can ensure that the filter performs effectively without instability or excessive resource use.